Hey guys, so I wanted to do some more examples for you for integration practice. So we'll look at some examples for substitution, definite integrals, including some definite integrals where you do have to do some substitution as well. And when we're doing definite integrals, that'll mean we're using the fundamental theorem, and an area as well. So FTC there is fundamental theorem of calculus, for where we have to evaluate those definite integrals. Okay, so a couple examples first. Let's see. I think I'll start with this left one here, is how it's set up. So it says the integral of 4x times the cube root. Now be careful here. This 3 is on the cube root, not a 4x cubed there. Cube root of 3 plus 4x squared dx. Okay, so we'll have to think how to handle this. It's too complicated to use any of our rules that we'd just use from the power rule or something like that. We've got 4x and then this cube root, so we've got really a product of two functions there, but again, we don't have a product rule for integration, so there's got to be some other way of handling it. So substitution is our way to go. That's our tool that we've got to handle these ugly functions with for now. Alright, and in this case, I think the correct substitution would be the inside of that cube root, 3 plus 4x squared. So first we might think to rewrite it. Rewrite that cube root as a 1/3 power. And there's our u, 3 plus 4x squared. Again, something raised to a power is usually a good candidate for our u. And take the derivative, we get our du. Anytime we make a substitution, not only do we need to change our x's to u's, but the dx there needs to change to a du as well. So du, the derivative would be 8x, and then tack on the dx there. We don't have 8x dx, but we do have 4x dx. Alright, so that's really 1/2 du. Now there's several ways we could have handled that. Could have pulled out the 4 and just looked for a way to make that x. That would be 1/8 du, would just be x dx. And then we have 4/8, and that would give us that 1/2. Or if you want to try to make exactly what we do have, we could divide by 1/2 and get to that 4x. So there's several ways again to handle that. But this is the way that kind of would give us the direct substitution here. Alright, so we get that 1/2 coming out from our 4x dx was 1/2 du, and then the rest of it is u to the 1/3, or 3 plus 4x squared to the 1/3, so u to the 1/3. And then the du is taken care of along with that 1/2. 1/2 du is the rest of it, 4x dx. Okay. And then we can integrate like normally. We've got our power rule to handle that u to the 1/3. So we'll increase that power by 1, 4/3, and divide by that power, or multiply by its reciprocal, that's 3/4. Alright, so that's 1/2 times 3/4, multiply the tops and bottoms, and we get 3/8 times 3 plus 4x squared. That was our u, putting that in for the u to get our original x's back. Since we made up u, we don't want u's in our answer, we want x's in our answer. And all of that to the 4/3, and then plus c. Okay, so we'll try a similar example here, some more substitution. Again, we don't have a quotient rule for integration, just like we don't have a product rule, so there's got to be some other way of handling some quotient like this. Alright, this one looks like, well, let's see, we've got big parentheses down here and then cubed, so 3x squared plus 12x, and all of that is cubed. So that's probably our best candidate for a u. But the problem with that is we're going to have to somehow make the rest of this show up in here. X plus 2 needs to be part of, well, the other part of our substitution is that du. Alright, so do a little rewriting first maybe. Bring that 3x squared plus 12x cubed that's in the denominator up to the top as a -3 power. We'll just get us ready for that substitution. Alright, u is 3x squared plus 12x. Alright, now go ahead and think about what the du is going to be before I click and make it show up here. Take that derivative of u, and we get 6x plus 12 dx for our du. Okay, remember, tack on that dx because that's going to be part of that substitution. Alright, now again, we don't quite have exactly the du. We don't have 6x plus 12. What do we have? We have x plus 2 dx. So how can we make x plus 2 dx show up in that du equation? Dividing by 6 would do that for us. factoring out that 6 if you like, and then dividing by it. So we've got 1/6 du is the leftovers there, the x plus 2 dx. Okay, so we'll make that substitution then. Our 1/6 du goes in for the x plus 2 dx, and the rest of it was our u to the negative third power, u to the negative 3. And we're ready to use our power rule. Alright, increase that power by 1, u to the negative 2. And then we've got dividing by that power, or dividing by negative 2 is the same thing as multiplying by negative 1/2. And then we'll put our u's back in, and I went ahead and sent that back down to the bottom there, so that negative 2 power means squared in the denominator. So we've got a negative 1/12, that's 6 times 2 on the bottom, times our u, 3x squared plus 12x squared, and again in the denominator from that negative 2 power. Okay, feel free to kind of pause at any time here as we go along. Since I'm not writing along with you, I might go a little faster than you want to write, or just watch as you go, and then you can go back and take some notes later on it if you want. Okay, 2 more here. Substitution, this time with some integrals that may show up with exponentials and logs. Now you won't know that ahead of time as you're trying these, but we'll see when those things start to show up here. Okay, so first one, 4x times e to the x squared dx. Okay, candidates for our u would be anything that's raised to a power, anything that's in an entire denominator, and the third thing that we talked about was anything in an exponent there. Okay, we know how to handle e to the u du, so if we can get it to look like that, that might be good. Alright, so we've got e to the x squared, so let's make x squared our u. Find that du. It's going to be 2x dx. Just a regular power rule for derivatives there to find that du. We don't have 2x dx, we have double that. Again, there's several ways you could handle that. If you wanted to, you could pull out the 4, and then x dx would be 1/2 du, but you notice 4 over 2 out front, and that would then be that 2. I like to kind of make what we do have show up, and that's one way of handling that. There are other ways though. Alright, so we don't have exactly du, we don't have exactly 2x dx, but we do have 4x dx here. Okay, oops, spoiling it. So we have 2 du, that was from the 4x dx, and the rest of it is just e to the u, e to the x squared. So e to the u du, and that's our goal anytime we have those exponentials in there, at least for now, is to get to e to the u du, because the integral of e to the u du is itself, and the 2 can hang around out front, so 2 e to the u plus c is our antiderivative, and then we'll put our u's back in there. Okay, so u was x squared, and there it is. Alright, let's try this next one then. We've got a fraction this time. Integral of x plus 2 divided by 3x squared plus 12x. So think about what a good candidate for that substitution might be. Again, sometimes there may be some other tricks that we could use. For instance, if that were just an x squared on the bottom, or just a 3x squared even, we could go ahead and divide both of those pieces by that, split that up into 2 integrals then maybe, and handle it that way. But here with that addition on the bottom of that fraction, we're a little bit out of luck. And it's probably the best thing to do some substitution here. There may be some rewriting that we can do sometimes, but in this case I think substitution is the best way to go. If that denominator were a little bit simpler, we could break up that fraction and go that way. Keep in mind though, you can never break up addition in that denominator. We can only break up the numerator into 2 fractions. We can't break up that denominator into 2 fractions. When you add and subtract fractions, you add and subtract the top. So if we're going to break it up, we can only break up the top as well. Alright, so substitution is the way to go here, and here we see that the denominator is probably our best choice for a u, the entire denominator there. So our goal in doing that is to get to 1 over u du, and think back to what our antiderivative of 1 over x dx was, or 1 over u du. That was our natural log integral. So find our du, You notice that's the same u as the previous problem on the previous slide. Alright, so 6x plus 12 dx. Again, we don't have 6x plus 12, we have x plus 2, so somehow we have to make that show up. So pulling out a 6 and dividing by that would do that. So we get 1/6 du equals x plus 2 dx, which is what we do have, the top, and then that dx will be 1/6 du. So we'll bring that 1/6 out to the front, and then the rest of it is 1 over u. Our entire denominator was our u, du. And the integral of that, or the antiderivative, is natural log of the absolute value there. Again, those absolute values I'd like to see on there, but if you forget it, I'm not going to worry about it too much. You just have to remember that anything that goes in there would have to become positive in order for that natural log to make sense. And so we'll put our u back in. 1/6 times the natural log of the absolute value of 3x squared plus 12x. Okay. Actually, I was thinking that 3x squared plus 12x might always be positive, but I think there may be some places where it's negative, so we'll leave it at that. Alright. I think next we'll switch to the definite integrals, so finding, whether we realize it or not, finding some areas, but we'll do some area problems as well at some point. The definite integrals, so using the fundamental theorem to evaluate some definite integrals. I think I have 3 on this page actually, only 2 are showing up for now, but I think we'll end up doing 3 of these here. Alright, so first the integral from -2 to 4 of x squared dx. Alright, so again, whether we realize that or not, that's really the area under the graph of x squared, under our regular parabola, if you want to think of it like that, from -2 to 4 on the x-axis. So from x equals -2 to x equals 4. Okay, if you wanted to sketch a little graph there, you can kind of imagine finding that area. I think that's always above the x-axis, so everything that we're counting here should end up being positive as we count that area. Alright, so simple integral, just our regular power rule, no substitution or anything required. So we'll add 1 to the power and divide by that power. Get 1/3 x cubed. And then we're not integrating anymore. We've taken our antiderivative, so that integral symbol goes away. I should say that goes for any of the previous problems as well. Let me back up a little bit. Notice in the previous problems, as soon as you actually take that antiderivative, that integral symbol goes away on the next step, right? It's just a technical thing that we're doing, but this is saying take the antiderivative. Once we do that, we don't need that symbol anymore. If you want, it kind of turns into the plus c, if you will. The du goes away as well, right? That's what we're talking about. After you integrate, that integral symbol and the du or the dx end up going away, and we get our antiderivative there. All right. All right. So with that in mind, let's go ahead and keep going with this one. All right. So add 1 to the power and divide by that power. 1/3 x cubed, and then we want to evaluate that from -2 to 4. But our fundamental theorem of calculus, FTC, tells us how to evaluate that. So we'll put in 4 first, put in the top limit, and then subtract what we get when we put in that bottom limit, -2. So 1/3 times 4 cubed minus 1/3 times -2 cubed. Alright, so now we have all numbers in there, we're just evaluating. We've taken care of our x, and we just need to simplify and see what number that actually is. Alright, so that ends up being 64 for 4 cubed, so 64/3 minus -8. -2 cubed is -8. So minus -8 cubed, over 3. 64 over 3 minus -8 over 3. So let's see, we've already got a common denominator. We could add the tops there. Minus the negative would turn into addition. That's 72 over 3, which is 24. Okay, so that whole integral ends up being 24. Or again, if you like, if you want to think of this as the area under that parabola from -2 to 4. We'll do some area problems in a little bit, though. They'll have some pictures to go along with them. So 24 square units there, if you want to think of that as an area. Alright, next one, I told you, I think I said there'd be 3 of these here. Here's the second one. Integral from 0 to 3 of e to the x dx. Again, I'm trying to keep these relatively simple, so no substitution required, but we'll get to ones with substitution in just a second. Let's see how that changes things. Alright, so antiderivative of e to the x, and then we'll worry about our fundamental theorem to take care of the integral from 0 to 3. So integral or antiderivative of e to the x is itself, so e to the x from 0 to 3. And what that means, what we'll do is plug in the top limit. So we'll put it in for the x, and we get e cubed minus e to the 0. Put in that bottom limit. And e to the 0 I think is 1, so we get e cubed minus 1. And throw that in the calculator, and you get a decimal approximation there of 19.086. Okay. Now I don't want you to get confused here. We're not always going to plug into what was inside that integral originally. It just happens in this case that antiderivative of e to the x was e to the x. Notice we put in the 4 and the negative 2 into something different here, not x squared, but 1/3 x cubed, because that's the antiderivative. I originally had this one listed first on this slide, but I thought that would be not the best one to start with, because it looks like we're plugging it into the original function there, but that's only because this is the one function, the one special function, our e to the x, our special exponential function, that who is its own derivative there. Sorry, an antiderivative for that matter, and that's what we're using here. Alright, so let's try one more. Integral from 1 to 4 of t cubed minus 3t squared plus 1 over t dt. Maybe go ahead and pause this one and try that one. This one mixes together a couple things, but no substitution or anything required. So pause here and see if you can handle that one, and then when you come back we'll work through it here. Alright, so we want to integrate, and we should get 1/4 t to the 4th minus t cubed, so that's increasing that power by 1, t to the 4th, and then dividing by that power. Same thing here, but we had the 3 hanging around, so the negative can hang around as well. Increase that power by 1 and we get t cubed, but 3 divided by 3 becomes 1, so minus just t cubed. And then the antiderivative of 1 over t would be natural log of the absolute value of t. Alright, and then all of that is going to get evaluated using our fundamental theorem. We'll put in 4, we'll put in 1. One thing to notice there is that those absolute values, well, the things that we were putting in anyway were positive, so we can go ahead and take off those absolute values as we put those in, because they're already positive. But if that were -1 to -4, or -4 to -1, if we were going from left to right, then we'd end up taking those absolute values there. Alright, so here we go. 1/4 times 4 to the 4th minus 4 cubed plus natural log of 4. Just evaluating all the way through, putting in 4, and then we'll subtract what we get when we put in 1. Okay, I think I have a little bit of a simplification step here. That's 64. That ends up being 256, but then divided by 4, so 64. Minus 4 cubed is 64 as well, so those will actually end up giving us 0. Plus natural log of 4. Minus 1/4 times 1, minus 1, and then plus 0. Natural log of 1 is 0. Alright, so that gives you natural log of 4, that's minus -3/4, so that's plus 3/4, and the calculator can get you an approximation of 2.136 for that one. Okay, so that mixed together a couple rules, but everything was added or subtracted there, so we can just go right through and integrate each piece as we're going, and then same deal with the evaluation. Okay, so now I think we'll try some of those, but with substitution thrown in as well. And the nice thing about doing these with substitution is that we don't have to do that extra step at the end of putting the x's back in there, but the price that we pay for that is that we'll have to change these x numbers to u numbers when we do that substitution. This is the way that I like to handle it. There are other ways of handling it, but I think this is the cleanest and simplest way to handle it as you go. Okay, so what substitution do you think is required on this first one with the square root over here? I think the inside of the square root is the best way to go. So there's our u, 1 plus 2x squared. Alright. Anytime we have a u, we'll need a du. So in this case that's 4x dx, derivative of u. This is 2 times 2, that's 4, and then x to the 1. So 4x dx. Alright, and then 1/4 du is what we do have, x dx. Alright, so far we're going to have a square root of u in the denominator, or I think we'll maybe rewrite that as a power. What power will that be? That'll be a square root, but in the denominator. So that's a negative for the denominator, and then a 1/2 power for the square root. So -1/2 power on u there. Alright, but there's one more thing that we have to change. We've got our x dx, we've got our square root of u in the denominator, but those limits of integration are x numbers. They go with the dx, so we need to make them go with the du now. So we'll put those in for the x in our original substitution, 1 plus 2 times whatever it is squared, and then those will give us our u's. So I think what happens there is when x is 0, we get 1 plus 2 times 0, so we get just 1, u is 1. And when x is 2, we get 1 plus 2 times 2 squared, that's 2 times 4, so that's 8. 1 plus 8 is 9. Alright, so our new integral with u's in it is going to go from 1 to 9 now instead of from 0 to 2. We're changing everything over to u's, including those limits of integration. Alright, so we get 1/4 du from our x dx that we originally had. And I said that square root in the denominator would be our u to the negative 1/2, negative for the denominator, 1/2 for that square root, and now from 1 to 9 again. Okay, so we'll integrate, take our antiderivative of u to the negative 1/2, we get u to the positive 1/2, alright, increase that power by 1, and then divide by that power. Dividing by 1/2 is the same thing as multiplying by its reciprocal, that's 2. So we get 1/4 hanging around out front times 2. And I'm going to go and write that as 1/2 square root of u. U to the 1/2 is square root of u, this time not in the denominator because we've added 1 and now it's positive. And then we're evaluating that from 1 to 9. So put in our 9, put in our 1. You notice those are perfect squares. So we end up with 3/2 minus 1/2. And 3/2 minus 1/2 is 2/2, and that's 1. So all that to get 1. What we got there. Alright, again, you notice the difference here. When we do that substitution with the definite integrals, we don't have to put those x's back in there. And in fact, we don't want to put those x's back in there as long as we've changed those x numbers into u numbers. If you do put the x's back in there, we wouldn't want to use 1 and 9 anymore. We'd want to go back to using 0 and 2. So you're making extra work for yourself there if you try to put those x's back in there at the end. Alright, we've kind of transformed this entire integral into an integral about u's, and the x's don't have to come up in there anymore because we're looking for a number and we found that number here. Alright, so let's try the second one. So it may be a little bit trickier to spot the substitution, but we think about what could be our substitution there. Our hints for things to be substitutions were things that are in the denominator. X being our u wouldn't really help because then du would just be dx, and we're just changing the variable there without making any substantial changes. What else? Things inside of exponents. There's no real exponents there. Inside of an exponent like on an e. We don't have any e's showing up here, so I don't think that's what we want. And then things raised to powers, and we do have something raised to a power there. That natural log is raised to a power. So I think that's our best candidate for u. And if we're thinking ahead a little bit, then what would the du be? I'll put it up there in just a second. But if u is natural log of x, what would du be? What's its derivative, right? Alright, so if u is natural log of x, du is 1 over x dx. And sure enough, that's what we have. We have 1 over x, it's in the denominator, dx. Alright, so that x in the denominator and the dx will become our du. Alright, what's the last thing that we have to change though as well? If we're making a substitution on one of these definite integrals with the numbers, again these are x numbers, so we want to turn those into u numbers. Alright, so when x is 1, we'll put in 1 into our natural log of x. Natural log of 1 though is 0. Okay, that says e to what power gives us 1? E to the 0 power gives us 1. Alright, and then when x is e squared, what was our top limit there? Natural log of e squared, natural log and e are inverses, so the 2 comes down if you like, and we just get 2. Or what's the power on e to make e squared? Well, that power better be 2, and there it is. Alright, so now our integral will go from what to what? It was from 1 to e squared, now it's going to be from 0 to 2, and what is our integral? Well, it's u cubed, and then the rest of that is taken care of by our du. An entire fraction there of over x dx is our du. Alright. Okay, so then we'll go ahead and finish that out. Notice we get a much simpler integral now. Don't have these complicated e squareds and don't have these complicated natural logs, and we'll never see those again because we've transformed the entire integral into a u integral. Don't have to put the x's back in on these definite integrals as long as we change those limits of integration. Alright, So we add 1 to the power, get u to the fourth, divide by that power, 1/4, multiply by its reciprocal if you want. Alright, and then we'll evaluate that from 0 to 2, so that means put in the top limit, put in 2, and then put in the bottom limit and subtract, put in 0. Let's see, 0 to the fourth is just 0, so I think this whole second part will just go away. We're subtracting 0 there. And then 1/4 times 16 gives us 16/4, and that's 4. Okay. And I think I've got 2 more slides, so 4 more examples here. And these will be dealing with area. Okay, so 2 area problems. The first one is to find the area between the graph of 50 minus 2x squared and the x-axis. All right. It's a little bit of an issue there that they didn't give us the boundaries on this one. Or I won't lie, I didn't give you the boundaries on this one. All right, so we're going to need to find those boundaries. All right. Well, if we're looking for between the graph of 50 minus 2x squared and the x-axis, we want to know where that graph touches or crosses the x-axis so that we can figure out what that boundary looks like. If you want to think of, kind of get a little picture in your head first of what that graph might look like, it's going to be a parabola because of the x squared. It's going to be facing downward because of that negative, and then that 50 means it's going to start way up at y equals 50. So it'll be a downward facing parabola starting way up at 50 and then working its way down. So if we're trying to figure out where it touches the x-axis to figure out these boundaries, that means where is it equal to 0. So we'll set that function equal to 0 to find where it touches the x-axis, finding its x-intercepts, and then we'll solve there. Several ways to solve that. You could factor out a 2 and then do some more factoring there. I'm just going to try to solve it by getting that x by itself since we don't have any x terms in between there. So 2x squared equals 50, moving 2x squared over to the other side, or kind of switching sides there as well. Divide by 2 and we get x squared equals 25. And that's x equals, make sure you get both of them, plus or minus 5. Take the square root of both sides. When we do that, we've got to remember plus or minus. 5 squared is 25, and negative 5 squared is 25. So we need both of those, because we're going to need those 2 limits of integration as our boundaries. Alright, and sure enough, that matches up with the graph. I think the units here are 10 on our y-axis, so that goes up to 50. And then and that starts working its way down from there, downward facing parabola, and then these units are 1 each on the x-axis, so from -5 to 5. And that's this bounded area that we're talking about. We don't want the rest of this because that's an unbounded area. We just want this this area between the graph of 50 minus 2x squared and the x-axis. Alright, so that's the integral from -5 to 5 of 50 minus 2x squared dx, and that'll get us this entire area here inside of that parabola above the x-axis. Okay, so no substitution required on this one. We can just run straight through and use our power rule. 50x minus 2, let's see, times 1/3 x to the third. Increase that power by 1 and divide by that power, so we get -2/3 x cubed from -5 to 5. Again, no substitution, so we don't have to change those limits of integration there. And we'll put in our 5, put in our -5, put in 5, 50 times 5 minus 2/3 times 5 cubed, minus what we get when we put in -5, 50 times -5 minus 2/3 times -5 cubed. And those are different, you notice, because we're raising those to an odd power there, so those negatives are going to hang around. Now I think what happens here, if you might notice that we're going to end up distributing this negative through in some way or another, or just evaluating both and then subtracting. That'll do the same thing. So those negatives will actually end up becoming positive. And really what we're doing is we're counting this area twice. So kind of the area from 0 to 5, and then we're doubling that. There's some symmetric properties of that graph that we could take advantage of. So you could integrate from 0 to 5 and then double what we get. And you'll see that same kind of thing happening here in just a second. Alright, so you end up getting 1,000 over 3, though, is where you end up. So that's 50 times 5 minus 2/3 times 5 cubed. I think you end up getting 500 over 3 for this one, and then this is minus, and you get -500 over 3 for this one, so that ends up being plus another 500 over 3, and that's 1,000 over 3. Okay, and that's 33 1/3. Sorry, 333 1/3. So that's our total area there. It's a relatively large number because that graph goes all the way up to 50. So we've got a like kind of a width of 10. If this were in one big rectangle, it would have a width of 10 and then a height of 50, so that's 500, but we're cutting off the pieces that are outside of that parabola of that rectangle, if you will. So we get 333. That seems kind of reasonable there. Again, if that were a rectangle with a width of 10 across the bottom and a height of 50 up to the top there, it would be 500, so we have a little bit less than that. All right. One more, area under the graph of, one more on this slide, area under the graph of this function, 16x times the square root of x squared plus 16. This time I did give you some boundaries from 0 to 3. Alright, and what I want you to notice is that f of x is positive on this interval, or at least greater than or equal to 0. When x is 0, we get 0 squared plus 16. Everything in here will be positive. As we end up squaring, we get something positive plus 16, it'll stay positive. So that whole square root is going to be positive. And as long as x is positive, or greater than or equal to 0, then our entire y value will be positive as well. So f of x is greater than or equal to 0. It's equal to 0 at 0 when we put in 0, but it's positive there. So all of that area will get counted as positive, and we don't have to worry about counting some of it as negative and some of it as positive or something like that. All right. So here we go. Set up our integral from 0 to 3. Again, this time I gave you the boundaries of our whole function here, 16x times the square root of x squared plus 16. This one will require some substitution, I think. So go ahead and think about what you want to substitute. I don't know, did I give a graph for this one? No, I don't think so. All right. That graph ends up being a little bit complicated, not as simple as our nice parabola there. But we'll need a u inside of the square root, or inside of that power if you want. That's a 1/2 power. Is x squared plus 16. That's our best candidate for a u. Du then is 2x dx. Alright, keep in mind we've got a 16x dx there, so there's several ways of handling that. We also have to change our limits of integration. So from 0 to 3, we'll change to from 16 to 25. That's 0 squared plus 16. That's 16. And then 3 squared is 9, plus 16 is 25. So instead of from 0 to 3, our new integral will have from 16 to 25. We have our u to the 1/2. And then that 16x dx isn't just 2x dx, we have actually 8 times as much, so we get an 8 coming out. Or if you like, pull out the 16, and then we get a 1/2 du. 16 times a half would be 8. So a couple ways of handling that. You could factor out the 8 here and have a 2x dx, exactly our du showing up, or pull out the whole 16 and then divide by 2 and you get 8. Alright, then we're ready to just use our power rule. Again, we've changed our limits of integration along with the variable, so we won't have to see those x's anymore. A nice simpler integral left. Increase that power by 1, u to the 3/2, and divide by that power, or multiply by its reciprocal. Divided by 3/2 would be times 2/3. So I have 8 times 2/3 u to the 3/2, with u going from 16 to 25. Alright, so that's 16/3, 8 times 2/3. 25 to the 3/2 minus the same thing, 16/3 times our lower limit to the 3/2. 16 to the 3/2. Now that half power on each of those will mean take the square root. So I think what I'd do is write that as 5 cubed. The square root of 25 is 5, but we'd still have to cube it. And then 16, square root of 16 is 4, so we have 4 cubed there. Both of them times 16/3, and then we're subtracting. So I've kind of factored out the 16/3 there and written 5 cubed minus 4 cubed. Alright, and that ends up giving you 976 over 3. And that's 125 minus 64, and then multiply by 16, you get 976, and that 3 on the bottom there. So that'd be an exact solution, or in the calculator, 325.333, 325 1/3. So actually almost the same area here with a completely different function. I think this one ends up being a little bit taller of a function on that interval there, since we've got a smaller interval of x values there. Okay, so a couple more examples. Vary between curves. Maybe pause it here and look over those and kind of make sure that you've got that idea before we start looking at area between curves, and that'll be the last big topic in Chapter 5. Alright, so area bounded by the graphs of, on the left here first, x squared and x plus 2. F of x is x squared, g of x is x plus 2. Now the trick with area bounded by two graphs, with one of them not being the x-axis, is to figure out which one's on top and which one's on bottom, and then where they intersect as well, so that we know what our limits of integration should be. Okay, so where to go from x equals what to x equals what. All right, so it may help to draw pictures of those graphs, especially since these are relatively simple. X squared is our just basic parabola, and then x plus 2 would be a line with a y-intercept of 2 and a slope of 1. We'll see a picture of that in a little bit, but we can find those limits of integration algebraically first if you like. So we'll set the two functions equal to each other to figure out where their y-coordinates are equal, then their x-coordinates would have to be the same as well. So set them equal to each other. That ends up being a quadratic. X squared equals x plus 2, so move everything over to one side, get it set equal to 0. It ends up being able to factor, and we find two solutions where that happens, at x equals 2 and at negative 1. Alright, so I bet we'll integrate here from negative 1 to 2 to go from left to right. Alright, just to show you a picture of it, here's x squared in black, and then here's our line, y equals x plus 2, or g of x equals x plus 2 in green. And sure enough, it looks like they do intersect here at negative 1 and at 2. Now, sometimes, if you're given a graph to begin with, you may be able to spot those limits of integration from that. But if we're not given a graph, then setting up that equation there, setting them equal to each other to find where they intersect, would be a good way to go. All right. Now, the other trick to these area bounded by two curves, or area between two curves, is to figure out which one's on top and which one's on bottom. Well, in this case, it looks like in between negative 1 and 2, that's our bounded part. The other part's unbounded. This would keep getting bigger and bigger. We couldn't find a finite area for that. So we want this bounded part, this kind of, I don't know, curved piece on the bottom with the line on top. And that spoils it there, but which one's on top? The line is. So g of x is, in that case, the green one. It's x plus 2. And then we'd want to subtract the one on the bottom, f of x, x squared. All right. So there's our integral from negative 1 to 2, from left to right. And we do top minus bottom. So x plus 2 on top, and then minus the bottom, x squared there. And then all times dx. Just to say that we're integrating with respect to x. Alright, there's really no combining like terms that we can do on this one. So just integrate straight through. You get 1/2 x squared for the x. Take its antiderivative. 2x for our 2 is an antiderivative. And then minus, keep that minus there, increase the power by 1, we get cubed, and then divide by that power, 1/3 x cubed, from negative 1 to 2. Again, the reason we need top minus bottom there, I'll just re-emphasize that, is that we want to keep the inside positive so that we're counting that area as positive. If we did bottom minus top, we'd end up getting a negative sign on what we've got there, because bottom minus top would be something smaller minus something bigger. We'd end up getting a negative y value there, and that would give us a negative area. Okay, so then we'll plug in our 2, plug in our negative 1. I've written that all out here. And then the rest of it is just some arithmetic. Calculator could help you out on that. And you end up with 9/5 overall for that one, or 4.5. Okay, that's 2 plus 2 times 2 is 4, so I get 6 minus 8/3. Okay. How do we get? Oh, we'll see. 6 minus 8, oh, there's where the half is coming in. That should be 9/2, I'm sorry. Let me fix that here. Okay. Change that to a 2. Sorry. So 9/2 there, not 9/5. That gives us 4.5. Something look funny about that. Alright, so you get, let's see, 4/2, that's 2. Plus 4, so far we're at 6. Minus 8/3, I think that 8/3 will end up, we'll have some help with that on the other one. So we've got 6 minus 8/3 there, just keep that in mind. Or write it down. 1/2 times negative 1 squared. Negative 1 squared will be positive 1, so we just have plus 1/2 here. That's where our half is going to come in. Minus 2. Alright, let's see, we had a plus 2 over here. Well, that's a minus and negative 2. And then, let's see, that negative 1 cubed will still be negative 1, so that'll flip that sign to a positive, so plus 1/3. Now keep in mind we had, what did we have? We had negative 8/3 over here, minus positive 1/3. So combining those, we end up getting 9/3, or 3. Alright, and then we can add up the rest of that. You do end up getting 9/2 there. One typo in the whole thing. 4.5. Okay. Switch back to my arrow. All right, so that area ends up being 4.5. And what we've done there is actually pretty powerful. We found this bounded area that's a curved figure, and we found the area of it. That's something that we couldn't do with regular geometry, so we need calculus to find that. And there are big applications of these definite integrals. We don't really get to see them other than finding this area. But there's bigger applications there other than just finding these areas of weird shaped things. But it's our first big application that we get, and that's what we've got time for in the course. Okay. So one more that I'll let you try here. Area bounded by the graphs of x cubed and 4x. And I'll go ahead and give you the graph on this one. All right, there's x cubed in red. Okay, our S-curve type graph. And then there's 4x in green. So a line with a slope of 4 going straight through the origin there. If you'll notice, this one's a little bit different. We've got kind of two regions there. One on the left side down here in the third quadrant, and one on the right side up here in the first quadrant. And what happens is, well, the top and bottom kind of switch there as they intersect at the origin there. So first, on the left side, on the top we've got x cubed, and on the bottom we've got 4x. So think about how that integral will be set up. What minus what? In order to make something positive, we want to do top minus bottom. So we should have x cubed minus 4x on that side. And then on our other integral, if we break this up into two integrals, we'll have 4x minus x cubed. 4x on the top minus x cubed on the bottom. So that'll be how we'll set up those integrals. We need our limits of integration. You can probably spot them from the graph here. It looks like at -2 these are intersecting, and then we get an unbounded piece down here that's not pictured. Alright, so this first one should go from where? -2 to 0. You can either check that those are equal at -2. -2 cubed is -8, as is 4 times -2, you get -8 as well. So that is indeed that intersection point. And then I think the same thing happens over here at +2. So our second integral will be from 0 to 2. Alright, if you have trouble spotting those from the graph when it's given, we can find those intersection points just like we did last time. Set those two functions equal to each other. That's a cubic function, so we want to get 0 on one side again. And do a little factoring. And some more factoring will get us x plus 2, x minus 2 there. And we get our three intersection points at -2, at 0, and at 2. Alright, so go ahead and try to set up those two integrals for this one. Again, there are some tricks maybe with symmetry here. We could find one of those, and I think that those are definitely going to be symmetric. We've got both odd functions here, if you'll remember that property. So if we spin around the origin, we get the same shape for both of those. So this area should be equal to this area. So we could find one of them and double it. Since we're just starting out on these, I'll just set up both of those with you. So from -2 to 0 first, and again we want top minus bottom. And on that side, on the negative side, that's x cubed on top and then 4x on the bottom. The cubic graph on top, the line on the bottom. Alright, and then plus the integral from 0 to 2 on our right side here, and then they switch on that side. So 4x minus x cubed. And then go ahead and try to integrate. No ugly substitution on these. I'm not going to try to throw that in there on those, but as we've seen, we could do some definite integrals or maybe some simple area ones with some substitutions. But on these area between curves, I'll try to keep it to one concept at a time here. Okay, so go ahead and integrate there using your power rule. Add 1 to the powers and divide by those powers. You should get 1/4 x to the 4th minus 2x squared on the first one from -2 to 0. Keep those limits of integration. And then just the opposite on the other one. 2x squared, add 1 to the power and divide by 2. We get 4 over 2. So that's 2x squared minus 1/4 x to the 4th again. You just have those in the different order there. Top minus bottom was different on each of those. This one from 0 to 2. And then the rest of that is evaluating. The nice thing about putting in 0 into these is that we'll actually get out a big 0 from those. And then putting in -2 and actually putting in +2, those both give you the same thing when you do that, because we've got even powers there, so those negatives and positives will end up adding. So let's see what happens here. When you plug in all zeros, you're going to get 0 out of that. All those x's becoming 0. Minus, we'll see what happens with this one, but -2 to the 4th times 1/4. I think that gets you 8. That's 16 over 4. So 8, no, 4 on that, sorry. This one gives you 8. Minus 2 times -2 squared will be 2 times 4, and that's 8. So you get 4 minus 8 here. That's negative 4, but that gets counted as negative because we're subtracting that bottom limit plugged in. All right, and then here's our second integral, added, plugging in positive 2 minus plugging in 0. So that gets you a big 0 for the first part, minus, like we said, 4 minus 8. That's minus negative 4, so you get positive 4. So this whole area of this left piece is positive 4, and sure enough, the area of the second piece, this 8 minus 4 minus 0, is also 4. 8 minus 4 gives you 4 as well. So we have 4 plus 4 overall, and that gives you a total area of 8. Again, there could be some shortcuts there of doubling the area of one of them, and that would be another way of finding that. But this gives you a little bit more practice with that fundamental theorem and the integration as well. And setting up and making sure you get top minus bottom right on both of those. Alright, if you slip up and get a negative area because you did bottom minus top on accident, maybe put some double arrows to say that you're switching those, and then just switch that negative to a positive when that happens. But make sure that you've got the right limits there. For instance, if we had tried to integrate from negative 2 to 2 here, without seeing that it switched at 0, what would have happened? We would have gotten negative 4 for one or the other, depending on which one we call the top, which one we call the bottom, since they switch at 0 there. That's the reason for needing to split it up into 2. We would have gotten maybe a negative area for this one, a positive area for this one, and we would have gotten a total integral of 0 there. But that's clearly not the area bounded. There is some area there, and it ends up being an area of 8. But if you end up counting this one as negative and this one as positive, we end up getting 0 there. So you have to be very careful with how you set those up. Otherwise, some of that area can end up canceling out with each other. Alright, so hopefully that helps a little bit, gives you a few more examples, several more examples actually, of those problems that we were working on last week, and we'll get you ready for the test next week. Let me know if you have questions on any of those. You can reference these in your email and tell me which slide it was on and which problem, and I'll be glad to help you out with those if there's any other questions that you've got. Alright, thanks for watching.